Okay, in this lecture, we're going to introduce molecular spectroscopy and talk about the energy level spacings between different types of motion or energies in a molecule, whether that's molecular vibration, molecular rotation, or electronic rearrangements. And so, molecular spectroscopy, we've covered atomic spectroscopy in previous videos. Go back and watch that to get caught up to speed. But molecular spectroscopy is much more complicated than atomic because of the different types of motion we now have to consider. Molecular spectroscopy, of course, is important because by just using light to investigate a molecule, we can determine things like bond lengths, bond energies, energy levels, vibrational frequencies, rotational constants, etc. Okay, and molecular spectroscopy, of course, is just molecules undergoing transitions due to radiation, i.e. light. Okay, so spectroscopy is always this light-matter interaction. Molecular spectroscopy, the matter is just molecules. Okay, and so this spectroscopy is really a fingerprint of the different quantum states in the molecule. Okay, because the transitions that a molecule is undergoing are between two quantized energy states, and light is providing that energy in this case. So a lot of times we, call a molecule's fingerprint its spectrum, what we're getting out of molecular spectroscopy. Okay, and the peaks that we'll see in our spectroscopy is due to sort of this attenuation, I'll call it, of radiation. Or flat out emission. And what I mean by that is, if there is light coming at your sample, you cause this increase, you cause this transition between this maybe ground state and this excited state. This maybe electron is promoted here. Then the light that reaches your detector over here is less. It has been attenuated because some of it got absorbed. And so in, say, UV-Vis spectroscopy, you're looking at, what is the change in the transmission of this light as a function of the wavelength. And only when the wavelength, of course, matches this energy gap do you cause this transition. Okay? So if it's an attenuation of radiation, it's like this. Of course, if the molecule is excited somehow, and it's in this state, well, it can just relax back down and emit all its own. And so you might just be looking at the emission here. So it's one of these two things that you're measuring in molecular spectroscopy. The peaks, of course, that you're measuring are at energies that are really delta energies, right? This is the gap here that we're measuring. And the delta energy there, the separation of those two states, is hc over lambda. Where lambda, of course, is the wavelength. Now, what makes molecular spectroscopy so difficult is the fact that molecules have not just electronic states, like we were sort of talking about here, but vibrational states, rotational states, translational states. Atoms don't have vibrations or rotations, right? Just electronic and translational, so their spectroscopy is more straightforward. The lines are sharper. It's easier to figure out what the atom is based on its fingerprint. But molecules, you get a lot of spectral congestion because there's a lot of transitions possible. And it's much more difficult sometimes to figure out what a molecule is just from its spectrum. But if you use complementary techniques, that might become easier. So let's think about the types of energy in a molecule. Okay, the first we're going to talk about is electronic. And electronic states are really how the electrons are organized. And this primarily is what we've been talking about for the past, 6 to 8 lectures. Solving the Schrödinger equation for a hydrogen atom or a many electron atom, or then molecules. Where are the electrons? What type of atomic orbitals are they in? SPDF. What kind of molecular orbitals are they in? Sigma, pi, bonding, antibonding, grad, ungrad. How are those electrons organized? That's electronic. And if it's a molecule, then we're talking, of course, molecular orbitals. Another type of energy, of course, is vibrational. And we've talked about vibrational energy several lectures ago. And the quantum system there is the harmonic oscillator. And we talked about the solutions to the Schrödinger equation for the harmonic oscillator. The energies, the eigenenergies you get out in the end, have to do with this reduced mass, quantum number n, and these are the energies of the harmonic oscillator. Right, the bond strength or the spring constant or whatever you want to call this, h bar, mu, and n, where n is your quantum number, 0 on up, 1, 2, 3, 4, etc. Rotational energies are a third type of energy. And for that, our model was the rigid rotor. We talked about that in both 2 and 3 dimensions. And the eigenenergies have various formulas. One of them looked like this. For a given radius, because it is a rigid rotor. Now, you can go through and calculate what are the energy spacings between two quantum states, n0 and n1, or ml0 and ml equals 1. And you can come up with the following. Because, again, in molecular spectroscopy, we care about delta E, the energy spacings for electronic, right? The energy separation of our molecular orbitals is much greater than the energy separation in our vibrational energy levels, which is greater than the energy separation for my rotational levels. Now, in each case, each of these delta E's, we can use light to probe the different types of energies. So out of the eigenenergy formulas for electronic motion, not motion, but electronic energy, vibrational energy, or rotational energy, we know the gaps between these types of states. And so on our energy diagram, maybe this is an electronic state. We'll call it electronic state 1. And maybe this is electronic state 2. And that's a pretty large energy gap. But for this given organization of electrons, that's what I'm communicating here with a certain electronic state, is a certain organization of electrons. For that given organization of electrons, there's vibrational motion. Okay? And so that vibrational motion is going to add to this electronic energy. And so I can have a vibrational state here. Maybe this is my 0 vibrational state. Okay, it's taken whatever amount of electronic energy I had, and it's added a little bit because now my nuclei are vibrating back and forth. Now, if I continue to pump energy in to that vibrational motion, well, I can have an excited vibrational level, That should be a flat line, of course. And if I continue to pump energy in, there should be another equally spaced level here, and so on and so forth, V3, V4, etc. So for this given organization of electrons, the nuclei here are vibrating back and forth, but the amount of this displacement is what's increasing here when I pump these vibrational states going up in energy. So that is vibrational states. And the spacing there is quite small compared to electronic states. Right? So here's my delta E vibration. And here's my delta E electronic. Now I need to talk about my rotational energy spacing, which is the least of the three. And so let's think about, for this certain organization of electrons, with the nuclei vibrating back and forth with this vibrational energy, there are different rotational states of that molecule. Rotating slowly, rotating medium, rotating faster, and faster, and faster. And we label these states J equals 0, 1, 2, 3, up to J equals 4. And keep going, but I'm going to avoid drawing all the other states so it doesn't get too congested here. But each of these vibrational levels, again, which are different amplitudes of nuclear motion for a given electronic state, each of those excited vibrations have their own rotational states to them. And this second vibrationally excited state, well, that has rotations with it as well. Each labeled J0 to J equals 4, but again, this really goes all the way up to J equals 100 and beyond. And that's just for the ground electronic state. There's the same kind of thing for this excited electronic state. There are vibrational states. And each of those vibrational states has some rotational states associated with it. And you can see now how complicated this is. Before, when we were talking about atomic spectroscopy, we were worried about term symbols and only these kinds of transitions right here. Right? Now think about all the different kinds of transitions, all the different arrows you can draw here to talk about promotion or movement of a molecule. Yes, you can move an electron from one organization to another. That is an electronic state. This separation in electronic states, well, that's pretty large. So therefore, the wavelength is pretty small. And this is usually about nanometers. And this is UV, or visible light. Okay, so electronic rearrangements in which you're moving an electron from one molecular orbital to a excited molecular orbital. Think back to the HOMO-LUMO gap in the previous lecture. That's generally a large change in energy. That's visible light, or UV light. Okay, so this is electronic spectroscopy, and we'll talk much more about that in the next lecture. There can, of course, also be vibrational transitions. And here lambda is kind of, well, it's larger than it was before for electronic. Why? Because the gap is smaller. And this is usually in like the millimeter, maybe micrometer range. This is IR light that corresponds to that wavelength. So we use IR light in vibrational spectroscopy. And we use UV or visible light in electronic spectroscopy. And well, rotations are really densely packed together. The change in energy here for rotations, still hc over lambda. Now, since it's a very small gap, my wavelength is pretty large. And this is maybe in the millimeter range to meter range. And this is microwaves. So microwave light is used for rotational spectroscopy. Okay, and this is sort of a dead giveaway for how our microwaves work at home. Microwaves at home are using microwave energy radiation or microwave light to cause water molecules to spin around faster and faster and faster. And that spinning water that you're causing to spin faster and faster and faster, well, that's going to bump into some other food molecule, impart some kinetic energy, and heat that molecule up. And so all you're doing in microwaves is energizing the rotations of water, but of course that water lies within other molecules or near other molecules, and so you end up heating up your whole food from just energizing the water rotations specifically. Now, one thing I should say about micro here is microwave does not stand for micrometer or micrometer. Right? It was just at the time termed micro because it was smaller than radio waves, which are more like kilometers. But they're really more like millimeters to meter scale wavelengths. Okay, so these are the different types of transitions you can cause. You could have a completely rotational transition. That's rotational spectroscopy. You could have a completely vibrational transition, and I'll draw an arrow here. You could have a completely electronic transition, and the length of that arrow tells you the separation of those energy states, and then tells you something about the wavelength needed. Now, in actuality, as we'll see in future lectures, usually these are all coupled together. So usually you are progressing from a certain organization of electrons with a certain vibrational motion, with a certain rotational motion, up to some other, perhaps excited vibrational level of this excited electronic state in an excited rotational level. And of course, there's selection rules for which ones you're allowed to go to and why, but we'll get to those and derive them specifically in future lectures. Now, allowed transitions here that are governed by selection rules, as I've said, we'll derive. But to derive and understand those selection rules, let's understand really quickly sort of a basic picture of what really light-matter interaction is. Okay, light-matter interaction is not the following. Here you might say, okay, here's a photon. We're going to think of it as a particle. And it's going to smash into this electron that I'm going to think about as this Bohr model of the atom. And when this photon smashes into the electron, it like physically imparts some momentum or something and kicks it up to a higher energy level, a larger orbit. Okay, that is a very classical and incorrect way to think about this. Okay, the photon doesn't like stick to the atom or impart kinetic energy. Okay, a wave picture is much more realistic. And in the wave picture, it's light being an electromagnetic field that is oscillating and alternating, that is causing a change in motion to perhaps the nuclei or the electrons. Okay, so if you thought about an HCl molecule, where the chlorine is negative and the hydrogen is positive, think about light being an electric field, and so this hydrogen chlorine is in this maybe positive and negative voltage, and the hydrogen is now repelled, and the chlorine is now repelled, and you're causing here a vibrational motion between the two nuclei. But then the electric field switches. And all of a sudden, now that you've moved hydrogen in here and chlorine in here, now you've shifted the electric field and you've alternated it. So now this is negative and this is positive. Well, the chlorine is still negatively charged, polarity, and hydrogen is positive. So now there's a motion back towards the edges. And so the type of motion you're causing here is this, in this case, vibrational motion of this contracting and elongating chemical bond. And so you can think about this oscillation of this hydrogen chlorine, this hydrochloric acid molecule, that you have induced from the light and the oscillating electric field. And that's the type of light-matter interaction I want you to think about. Right? As if this thing exists in between two plates of a capacitor, or two charged plates, I should say, where the voltage is oscillating because that is what is happening in light. It's an oscillating electric and magnetic field, and you're inducing this motion from this time-dependent electric field. That is what light is, an electromagnetic wave. So this is the useful conceptual picture of how light induces motion or energy change, whether that's vibrational motion here or the movement of electrons. Both are applicable. So with that sort of introduction to molecular spectroscopy, the different types of energy levels, how to think about light interacting and causing some of these changes, the different types of wavelength of light we might use for the different types of transitions, we'll end this lecture, and next time we'll talk specifically about electronic spectroscopy, the types of selection rules involved, radiative and non-radiative interactions, and build Jablonski diagrams that describe all the types of transitions we see in electronic spectroscopy. So that'll do it for this lecture. Stay tuned next time for electronic spectroscopy, and then beyond that, we'll move into molecular term symbols, lasers, phosphorescence, fluorescence, and expand on our Jablonski diagrams. That'll do it for this lecture. See you next time.